Hello everyone, welcome back to the channel and welcome back to the series of environmental engineering. And today we are going to see lecture number 12, which is on fluoride and nitrogen in water. So till now, till lecture 11, we have seen different water quality parameters, and today we are discussing further water quality parameters, which is fluoride and nitrogen. And so till now we have seen in full of our course, which is the things that are water demand, and then we saw the water sources from where the water is coming, and now we are working on the quality of water. So this is the next topic. Now let's move on to the next slide, which is, so we have the connection with the previous lecture here. So we are seeing the chemical water parameters, which is TDS, conductivity, pH, alkalinity, hardness. We have seen. Today we are going to see fluoride. Now we see here, the first question which comes to our mind is, can a chemical be both beneficial and harmful? So there is one chemical which is, if it is too little, it can be a problem. But if it is too much, then also it can be a problem. Okay. So this is fluoride. So the compound which we are talking about is fluoride. So fluoride, if has low concentrations, the concentration exactly, if I say, if the fluoride is below 1 milligram per liter, okay, then it's a low concentration. And if it is low concentration, then it uh, uh, creates dental problem. So if it is at the proper concentration, like around 1 milligram per liter, then it will protect our dental enamel. Okay. And if it is of high concentration, so high concentration means it's greater than 1.5 ppm. Okay. So if it is more, then it will create fluorosis. Okay. Fluorosis is the discoloration. It will discoloration, and it will make the uh, dental bones weak. Okay. So this is called fluorosis. So uh, if low concentration, uh, if it, so the range is between 1 milligram per liter to 1.5 milligram per liter. Okay. So will in this range we will get dental protection, so our tooth will be good there. And there is one more concentration, which is 5 ppm. So if it goes beyond 5 ppm, right? So if goes beyond 5 ppm, then also we will be getting fluorosis. Okay. So at high concentration, greater than 1.5, we will be seeing discoloration and something, but the range becomes more, that is greater than 5 ppm, then we'll definitely get fluorosis. Okay. So this is what uh, fluoride, if that is in low concentration, if that is in high concentration, will create. So the question is, what's fluoride? So it's the ionic form of fluorine, so we'll be getting F minus, right? So it's the ionic form of fluorine, and it is commonly present in natural water. And now, from where it is coming? So the sources of fluoride are natural sources and anthropogenic. Anthropogenic means human generated. Okay. So natural sources are weathering of rocks. So the rocks will be weathered, and then it will get mixed with sand, and then it will reach to the groundwater. Okay. So there will be groundwater interaction, and then fluoride comes to groundwater from the weathering of rock. That is natural process. And then anthropogenic is the industrial waste. So much of industries create a lot of fluoride that we are putting straight into the river, and then it's creating fluoride concentrations very high. Okay. So these are the sources from where the fluoride comes to the water. And then Why fluoride is important? We know that if it is of low, then also it's a concern. It's of optimal concentration, it will be beneficial, it will give dental protection. And then if it is high, then it will also be of concern, it will create fluorosis. Okay, and then we see here what's dental fluorosis. So you can see dental fluorosis is a condition caused by excessive fluoride intake during the period of tooth development, enamel formation. So at the tooth development, if people are taking lot of fluoride, will be getting the fluorosis disease. So excessive fluoride consumption is a cause, and during tooth formation, like up to 8 years of age, if we are getting more fluoride into our concentration, into our water, or anyhow we are getting more fluoride, then it will create this issue. So the normal teeth will look something like this, right? And if it is very mild attack of fluoride, like fluorosis, then we'll be seeing faint white lines on streaks. Okay, and then if mild attack, you will be seeing white, these opaque white areas, right? And then if it is moderate, you will see the yellow and brown stains mostly present in all the teeth. And then severe damage will be there, then you will be seeing extensive brown stains, and then pits also, a bit of uh, hollow incrustation will be there. Okay, so this is how fluorosis will show on the teeth. Now commonly the teeth will be affected something like this. So if you see someone's teeth like this, you can say that yeah, there were uh, fluorosis on there, and that too it's a mild or medium range of fluorosis. Okay, and the effect will be that hyper polymerization of enamel will happen, and it causes a change in color and texture of the teeth. Okay, so this is what dental fluorosis is. Now fluorides in drinking water, and specifically we'll be seeing how to measure. Okay, so for measurement of fluoride, we used colorimetric method. So we call it COLOURI metric method. So in this, we'll be doing color matching. So it is color matching technique. Okay, so what we are going to take? We have two chemicals. First is your zirconyl acid, ZIRCONYL, zirconyl acid, and then we have SPANDS, SPANDS. So these two chemicals, once combined, they give red color. They give a red color complex. Okay, now so this is a red colored complex. Now if we add fluoride, into this mixture, so if we add fluoride plus this mixture, so what it will be doing, this zirconyl acid will react to fluoride, so it will make something ZrF6 2 minus, and this is a colorless compound. So fluoride has a tendency to react with zirconyl acid, and it is a colorless compound, and it will just make the spands free. So we have free spands, right? So and spands is the so the red color complex will get uh, lighter, right? Because zirconyl and spands were initially creating a very deep red complex, and then you are adding the water, which is fluoride, which is heavily with fluorides. Then what you are doing is zirconyl and fluoride will create they will react to each other and they will form compound. That compound will be colorless and it will remove strands. So the more and more fluoride you are going to add, more the colorless will be the solution, right? So from this you can understand, if lighter the color, that means there was fluoride in the solution. And if we increase the fluoride concentration, the color will be more light, right? So this is how we measure the fluoride into the water, and it's a colorimetric technique. We measure it using a UV spectrophotometer, right? So this is what fluoride in drinking water is measured up how. Okay. Now, so we have a basic thing, that is fluoride is a one chemical parameter whose concentration can directly affect human health by, but another group of substances tell us something very different about water quality. So these are nitrogen compounds. So now we are heading towards nitrogen compound. Fluorides can directly tell us that if they are affecting human health or not, but nitrogen is something very different. So now we will head towards nitrogen. So we have to see why there is nitrogen into the water, how and why. So you see that there is a lot of organic compound in the environment. So we are throwing organic waste into the water. So human urine is of urea. Urea is nothing but made of nitrogen. So we are directly throwing nitrogen into the water. So a lot of nitrogen comes into the water due to organic compounds. So there is a lot of organic nitrogen into the water, and its concentration also should be under some limit. If it is more than that, then it can also create diseases, right? So that we'll be studying just after some time. So we get the water, we get the nitrogen in the organic form into the water. Now this organic nitrogen will convert itself to ammonia, and then ammonia will convert to nitrite, and then it will get converted into the nitrate. So we'll be seeing this in detail. But why nitrogen in water? It's due to the organic compounds which are all over present into the water, and also due to inorganic nitrogen which is already present into the atmosphere. We know, right? In atmosphere there is about 78% of nitrogen, but we have to see how that nitrogen will also be dissolved into the water. How can that happen? That's inorganic. So that also we will be seeing here. So in the next slide we have different forms of nitrogen. So we have organic nitrogen. So organic nitrogen is the part of organic compounds like protein, amino acids, urea, domestic sewage. We have animal and plant residue. We have decaying organic matter, and then we come to inorganic nitrogen. So the nitrogen which is present in inorganic form. So we get organic nitrogen, we convert that into the nitrogen gets converted that into the inorganic form. So the inorganic forms are ammonia or ammonium, and then we have nitrite, and then we have nitrate, and then other inorganic forms, simple nitrogen or something like that. So we have these compounds there, right? And now uh, we have, see here, so the organic nitrogen will get converted into ammonium, and then from ammonium or ammonia it gets converted to nitrite due to some bacteria that are present into the atmosphere. So those bacteria are nitrogen philic, we can say. So there are certain bacteria like Nitrobacter or some other bacteria, so that will be creating uh, generating from ammonia the nitrite, and then from nitrite they will generate nitrate, and then we have denitrification, and again we will be getting nitrogen gas. So we'll see, this is nothing but we call it nitrogen cycle. We'll be seeing that in detail. First, let's see, we have organic nitrogen. We also call it as free nitrogen, right? So it's free nitrogen, and if it is present into the water, it indicates there is a recent pollution. So it indicates there is recent pollution, right? And the sources will be protein, amino acid, urea, domestic sewage, animal waste, and organic matter, right? And the acceptable limit of this is 0.15 milligram per liter. So if the water is having more than this, that's not acceptable to us, right? So this is what organic nitrogen is. Now we also have the next, which is ammonia. We also call it organic ammonia, right? So this signifies that the presence of complex organic matter into the water. So if ammonia is there, we it is also denoted by like NH3, or if it gets converted, then it will be converted to NH4. These both are interconvertible, so we make this kind of sign between them. So NH3 is nothing but ammonium ion, right? So if ammonia is present, it signifies the presence of complex organic matter. So there will be complex organic matter present into the water, right? And this can measured by boiling the water sample. So if we boil and we boil it with the help of, so boiling, and we'll be adding some of strong alkali reagent. So there will be strong alkali reagent. So in the presence of strong alkali reagent, so the strong alkali reagent, in for example we have potassium. So if we boil it, potassium permanganate. Okay, so if we boil the water which is containing ammonia in the presence of strong alkali reagent, which is potassium permanganate, that means KMnO4, then we can see the gas will be liberated. That gas is nothing but ammonia, so NH3. So we can find ammonia from like this. Okay, so this is organic ammonia. So you have organic, so you have, for example, you have organic matter, right? And then you will be boiling it. So you will be boiling it, and then you will see, by adding KMnO4, you will be seeing that ammonia is liberated, right? So this is how you will be getting ammonia. And in between NH3 and NH4, what you will be getting, it depends on totally depends on pH and temperature. So this influence the distribution of NH3 and NH4. It can be, so the ratio of NH3 to NH4 depends on pH and temperature, right? So this is what ammonia is. Now we have a process called nitrification, and nitrification is nothing but, it's a biological oxidation of ammonia to nitrate. So we got organic ammonia, free ammonia, right? And from that free nitrogen, Fn, or free ammonia, we can say free nitrogen, and then from that we converted that to organic ammonia, right? Now this organic ammonia will be converted to nitrate. So nitrate is written by NO2 minus. So this is nitrite. So this is nitrite. Okay, so it will be converted to nitrite, and then nitrite will be converted to nitrate, NO3 minus, right? So the process of converting this organic ammonia to nitrate is called nitrification. So first organic ammonia will be converted to nitrite and then it will get converted to nitrate. So the total process of converting this organic ammonia to the nitrate till nitrate called it as nitrification. So basically you are doing oxidation, right? You have NH3, right, and then you are adding oxygen to that, so you are basically uh, doing oxidation of ammonia, right? And then oxidation is not chemically done, it's biologically done. So we have nitrification which is happening in two steps. So the ammonia in water, it's getting oxidated, and the we are not doing it chemically. There are some bacteria which convert it. So the bacteria which converts ammonia to nitrite is known as Nitrosomonas. Okay, so the ammonia which converts it, it is known as Nitrosomonas, right? And then we have so the ammonia is converted with Nitrosomonas, so it converted to nitrite. Now the nitrite oxidation will start in step 2, and then comes into the picture is Nitrobacter bacteria. So the Nitrobacter will, so the bacteria will convert nitrite to nitrate in water. Okay, so these are the conversions, and this process is called nitrification. So the process is known as nitrification, and we can see the overall reaction here. Now uh, this takes some time. So this is called nitrification, and the first compound of nitrification is nitrite. So we see nitrite here. So nitrite was denoted by NO2 minus. So nitrite is if it is present in the water, so we can say if it is present, the water is not at all uh, fit to use. So nitrite is highly dangerous. So if it is present, so we can say that there is partial decomposition of organic matter, right? So till now only Nitrosomonas has worked, and there is partial decomposition. For fully decomposition, it should be converted into nitrate. So if it is present, then we should know that there is a partial decomposition only. We need to wait for further decomposition. So partial decomposition of organic matter. Okay, and so it is highly dangerous into the water. So the limit will be 0 milligram per liter. So water should not have nitrite at like a bit of nitrite into the water. So it's an intermediate nitrogen species, right? Usually present at lower concentrations than nitrate. Obviously, indicates that there is ongoing nitrogen transformation happening, and can be problematic because of its health effect, and it's not very dangerous. It's not at all desirable to have its minimum amount of limit also. Okay, and how we will measure this, how we will measure nitrite is again color matching technique. So the measurement is again due to color matching technique, and the chemicals which we'll be using here is sulfonic acid plus naphthalene. Right. So these two will create a yellowish compound, and we need to match the different concentrations of this to get nitrite. Now this is what nitrite is. Now let's move on to the next, which is nitrate, also denoted by NO3 minus, and the sources will be mainly the source is fertilizer. So nitrate is a very important fertilizer, and that is used into the water, so into the soils, and from soils it gets penetrated into the groundwater. right? So fertilizers are very common source for nitrates. So its presence is not harmful, is not harmful, and up to a certain uh, higher concentrations, right? So the limit up to which it is not harmful is 45 milligram per liter. Okay, so up to 45 milligram per liter, nitrate is not at all harmful. But if it is present more than that, okay, more than 45 milligram per liter, then the infants can get disease. We also call that as uh, methemoglobinemia. So we also called it that methemoglobinemia, and it's in simple words we also call it as blue baby disease, right? So what's that? We can also see it in detail. So what is this? Nitrate and methemoglobinemia. So high nitrate in drinking water can cause this disease. We also call it as blue baby disease, baby syndrome, and nitrate. And then so oxidation was happening. So nitrate will be reduced to nitrite and further ammonia. So the this disease is nothing but in this, the blood increases and reduces the oxygen carrying capacity. If nitrate is present into the water, what will it do? It will reduce the oxygen carrying capacity of blood. So the symptom will be that the lips, skin, and nails will be in bluish color, and breathing problem will be there in the infants. There will be fatigue and weakness, and in severe cases, headache, disease, confusion, even death can also occur. So you have proper normal your hemoglobin nitrate, right? So if I, so you can see here, so you have mm, so you have the mechanism how nitrite causes methemoglobinemia. That is, you have a normal hemoglobin. So you have this hemoglobin will carry oxygen, right? Now nitrite what will do, it will oxidize the hemoglobin. So nitrite is there something like this will oxidize hemoglobin, and then globin forms here. So we call it as methemoglobin. So methemoglobin will be formed when nitrate is added uh, into the hemoglobin, right? And now if this compound is created, it cannot carry oxygen effectively, right? So it reduces the oxygen transport into the blood, right? Hemoglobin is no more carrying oxygen now, so it leads to hypoxia. Hypoxia is nothing but low oxygen tissue. So excess nitrite converts hemoglobin to methemoglobin, right? And it reduces blood's ability to carry oxygen. So this is what blue baby disease is. Now we got to know what's nitrate. So we knew all four forms of nitrogen, which is free ammonia, then we have free oxygen, then free nitrogen, and then we have free ammonia, organic ammonia basically, and then we have nitrate, and then we have nitrite, and then we have nitrate. So these are the basic compounds that's getting created into the water of nitrogen. So here we see nitrogen cycle. So nitrogen cycle is nothing but so the conversion of nitrogen into different compounds that we studied just now. So atmosphere is having about 78% of nitrogen, right? Now this nitrogen should be converted into the organic nitrogen, right? It's inorganic till now. The organic species, how they will use it to convert by by converting this to organic nitrogen. So we call this process of making inorganic nitrogen to organic nitrogen, we call it as nitrogen fixation. So nitrogen fixation is so in atmosphere it will be done by lightning. So lightning fixes nitrogen. It changes inorganic nitrogen into organic nitrogen. And in soil also there will be compounds, right? So in soil the nitrogen fixing bacteria will be there that will convert the inorganic nitrogen to organic nitrogen, because we are throwing inorganic nitrate, right? And the plants will observe that, and then they will make it organic, and then they will be using that nitrogen, right? So uh, there is in the soil there is nitrogen fixing bacteria. In the atmosphere there is lightning which is making it organic. Now there will be ammonification. So nitrogen conversion of atmospheric to ammonia. Right. Now we have ammonification. In this case, conversion of organic nitrogen to ammonia. So ammonification nitrogen fixation is atmospheric nitrogen and is converted into organic nitrogen, that is nothing but ammonia. And ammonification is the conversion of organic nitrogen to ammonia. So ammonification is done by bacteria. So organic nitrogen from dead organism and waste converts into ammonia, and then we get ammonium here, right? Also there is organic nitrogen, which is protein, nuclei, acid, ammonia, and this also due to ammonification gets converted into ammonium, and then ammonium will be converted into nitrate with the help of nitrification and with the help of nitrosomonas, and then it will be converted into nitrite, right? And then further nitrification will happen and nitrobacter will convert it into nitrate, right? And then it is getting converted. So nitrate is done. Now uh, after all the usage, there will be some bacteria that will denitrificate. So this is denitrification process, and this is then that is because organic in the nitrate state, ammonia cannot go into the atmosphere. We need to convert it into nitrogen so that it can go back to the atmosphere. So converting it back to the nitrogen is denitrification. So by denitrification is also done by certain bacteria, and then it is again there into the atmosphere, and then the atmosphere will be converted again into due to the nitrogen fixation. And then there is assimilation is also a process. Assimilation is nothing but, see here, absorption of inorganic nitrogen by plants. So plants directly can absorb inorganic nitrogen, and that process is known as assimilation. So and then they convert that inorganic nitrogen to organic nitrogen. So this organic nitrogen is now converted by plants, and then it will be changed into ammonia by ammonification. So and then this is how the cycle runs. So this is what nitrogen cycle is, and different compounds get converted due to different conditions or bacteria. So this is what we see here. Now can we compare the different nitrogen species? So we have organic nitrogen or ammonia, organic nitrogen, so or free nitrogen. So the formula is simple, nothing. And then major significance, it is in sewage or organic matter. Ammonia indicates there is a fresh pollution or toxicity. And then we have nitrite, this is nothing but intermediate oxidation product. And then we have nitrate, it is final oxidation product. And then we get it in groundwater and agricultural contamination. So with this we have finished with the fluorides and nitrogen. And in the next lecture I guess we'll be seeing the uh, oxygen part. So the oxygen, how much oxygen should be there into the water, DOD and all. So yeah, let's see that in the next lecture. I hope you got it. Thank you.